that worked. Okay, this is the first hour of Physics 1b for November 22nd. Today we're going to be talking about mechanical waves. So what is a wave? Well, I guess a simple way to start would be to use something like this. So you need two things for a wave. You need a medium and a disturbance. Let me write that down first. And when I say waves here, I'm talking about mechanical waves. So I guess I should put that part here too. So this is mechanical waves. There are another type of wave called electromagnetic waves that do not follow these rules. But mechanical waves need two things. You need a medium, something like, if this could be something like water. It could be, in the case of a guitar, it could be like a string. In the case of sound, it could be the air in the room. What other kind of waves are there? So think about that. And then you need a disturbance of the medium. When you think about waves, what do you think about? Troy says, so far so good, nothing on Wednesday because of Thanksgiving. Yeah, what are you talking about? No, we have a lab on Wednesday, don't we? The school's open on Wednesday. Thanksgiving is Thursday. I know a lot of schools, some schools will take a week off for Thanksgiving and some schools will take the Wednesday off, but no, we have a lab on Wednesday. We're doing like, I don't know, what is it this week? 8:15 maybe or something like that? I'll look during the break, just to remind you. You may not have something this week if you're in the latter half of the alphabet, Troy, because that's just how it's been going, but yeah. Holiday 15, huh? Okay. All right, so these are the two things you need for a wave. You need a medium and you need a disturbance. So you probably have all seen water waves, such as like tides coming in. That's an example of a wave that's going through the water, the tides. Maybe you've been out on a lake when a lot of waves are on the lake, or maybe you've been out on the ocean. You've seen the way that the ocean can kind of move up and down a lot. Heat waves. So that's one that is kind of a... I don't know. Maybe I'm just being too picky, but I think heat wave is kind of a non-scientific term or something like that. You know, where, you know, maybe, I don't know what you're thinking of, Matthew. You're thinking of like, people will say, oh, there's a heat wave passing through the area, in which they mean that the temperature kind of goes up. So radio waves is another one. That's right, Astro Lover. And a radio wave is different from these, actually. Because one of the unique things about a radio wave is that it actually just kind of can propagate through empty space. In fact, if you're, for example, if you're out in space and you wanted to communicate with people, like let's say you're the astronauts that work, for example, on the International Space Station, repairing it and doing things like that, when they're talking to each other, they have to use headsets, and the headsets have to be tuned into some radio frequency so you can talk to each other. And that's because waves like sound waves won't pass through empty space, but radio waves will. And that's because radio waves don't actually require a medium. They travel along electric and magnetic field lines, which if you take Physics 1C, you can learn a little bit more about that kind of stuff. But we were talking about mechanical waves, so these are kind of waves that you can actually physically see, I guess is what we could say. Waves that have some type of a medium and there's some kind of disturbance, and that disturbance can propagate through the medium. Anyway, going back to heat waves, I think that when people say heat wave, it's kind of a misnomer. When they're saying that there's a wave of heat coming through, they're just saying that it's going to be really hot, right? That's what they're saying. So it's kind of an awkward thing, especially since we're in this class where we're talking about heat a lot. The heat waves happens to be this thing. Anyway, but you've seen water waves before, probably. You've probably seen waves on a string. You can't see sound waves, but I guess maybe with appropriate instruments you maybe could, but you can't really see sound waves normally. You just hear them with your ears. What other kind of waves are there? Any other kind of waves you all can think of? Types of substances through which a wave can propagate? I can think of at least one that's not on here that you all probably have experienced some. So microwaves and radio waves are the same thing, Umair. They're all part of what we call the electromagnetic spectrum. So that includes, it's a good guess though. I mean, nothing wrong with that one. So microwaves, radio waves, light waves, infrared waves, UV waves, which come from the sun, an earthquake. There you go. So the Earth could be a medium too, right? Because an earthquake is a propagation of a disturbance in the Earth's crust that propagates through the Earth and creates, makes things shake and stuff like that. So earthquakes are an example of waves. So I'm just going to put down here what kind of things are mechanical waves. So we've said water waves, waves in the ocean, things like that. I think snakes are a good example too. Yep. Snakes use waves to move themselves along the ground, right? Those are like waves through their own body that kind of push against the earth and allow them to move along. Okay, so water waves, waves on a string, sound waves. These are all what we call mechanical waves, where there is a physical medium through which things pass. Sound waves, water waves, earthquakes. Oops. So earthquake was the one I was thinking of. What other kind of waves are there? Reality is that, like, as long as you have some type of a medium, there are always ways for waves to propagate through it. Your medium could be something like, I can give you a really simple example. So, like, if you take a sheet and you, like, stretch it over a bed, you can take one into the sheet and you could, like, send a wave down it, right? That's another example of something you could make a wave out of. Pretty much any type of object that can bend in any way can be made into some type of wave motion. The toy, like, Slinky thing is a good example of this too, where with a Slinky you can, like, stretch it out and you can push one side of it and you can watch as the spring will, like, vibrate a little bit. That's another type of a wave. So let's look at just some. These are demos of waves, not demos, right? But they're just little simulations of waves. So here what we have is, this is supposed to be like water here, and what we can do is we can click this button, and a little drop will drop down, and then you'll see a wave go out in a way that you've probably seen before if you've ever thrown a rock into a pond or dropped anything into, like, a sink full of water or a bathtub full of water. Anytime you have some amount of water, like in a pond, and you, like, throw a rock in the pond like this, then there'll be ripples that come out, right? I think usually you'll see a lot more ripples than this. Usually you're going to see something that's more like this, where you have multiple waves that are emanating out. So this is an example of a mechanical wave. And it has certain properties. In this case, there's going to be a maximum and a minimum, or a crest and a trough, that are indicated here by light and dark colors. We can go to a side view as well. I don't remember this. This is kind of cool. So here we can actually see what those crests and trough look like, I guess. So down here, there's a trough. You can see that it kind of, like, goes along. Up here you have crests, the height of the wave, and it kind of just travels along like this. And it maintains a form that you're kind of familiar with, which is somewhat similar to, like, a sine wave, right? Waves have properties of things like wavelengths. Can I get a... here we go. The wavelength of a wave is given as the distance between two successive crests, or it's also the distance between two successive troughs, which you can see here are the same distance. Like, this looks like this is about 2.5 centimeters, and this looks like this is about 2.5 centimeters. Now, we can change things about the wave itself. We can change the frequency of the wave, and we can change the amplitude of the wave. When we change the frequency of the wave, what's going to happen is that the drops are just going to drop faster. And as a result of that, the distance between the wave crests is probably going to change. So let's see what happens. So right now we have the distance between these wave crests is about 2.5 centimeters. I could probably do a better job of this. It's actually more like 2.6, isn't it? Okay. All right. Notice that I think even here, it's kind of hard to tell because of those letters, but even here, even though the amplitude of the wave, so amplitude is the height of the wave up and down, and wavelength is the length of the wave, left and right. So amplitude of the wave would be like this height here, from top to bottom. So you'd have to measure all the way from the top all the way to the bottom right here. So this is probably a little too much. But I wanted to point out that even though the amplitude of the wave is decreasing, like here the amplitude of the wave is shorter, and I bet even here the amplitude of the wave is even shorter. So the amplitude of our wave is getting smaller over time, which is an indication that the wave is losing energy. The amplitude of the wave is a direct measurement of how much energy it carries. So even though the amplitude is getting smaller, notice that the wavelength remains unchanged. The wavelength right here is still like 2.6 centimeters, and then we go to this point right here, the wavelength is still 2.6 centimeters. See how it's still right at the top of the wave and right at the top of the wave, and we can check the bottom right here. So one of the interesting things about a wave is that the frequency of the wave is entirely determined by this right here. Can you tell that? The drops of the wave, whether we look at it from the top or the bottom, every drop comes in and creates a depression, which creates a trough, and then the rate at which this drops down is directly related to the frequency, right? So if we increase the frequency, what we're going to see is that this is going to start dropping faster, and the wave will look differently as a result. I guess before I do that, what do you all think is going to happen to the wavelength of the wave? Remember, the wavelength is the distance between two peaks right here, or the distance between two troughs. If we start making the drops come down faster and by increasing the frequency, what's going to happen to the wavelength? Do you think it's going to get longer or shorter? Think about it and put your answer in the chat. Actually, just wait. A couple people already said things. So I was going to say wait and put your answer in. Okay, 2 people say wavelength is shorter. 3 people say wavelength is shorter. So think for yourself. See if you agree with them or not. And let's see what happens. So we'll just go ahead and directly increase this to maybe like right here, and let's see what happens. So before it was 2.6 centimeters. Oops, I push play. I think you all are right. I think it did get shorter. We're going to measure it here in a second, though. All right, there we go. So now we've got a lot of features of the wave. And yeah, it does look like it gets shorter by about from 2 to 2.6. From 2.6 to 2. In fact, the amount by which it got shorter, we could probably figure out, but we don't have a numerical value of the frequency. We just, on this arbitrary scale here, we increased it by like 3 notches. I don't know what that actually physically means. Does this allow us to test the frequency or something? Let's see what does this do? It's just a timer, right? Yeah, that's what I thought. Okay. What's this one? Water level. It's kind of an interesting one. What does this one look like if we try this? Do I need 2 different, the water level relative to a point, I guess, right? So, but I can't. Oh, I guess it just does that, and then it makes music as it plays. That's kind of funny. I think it's plotting the water level at 2 different points. Am I crazy? That's kind of cool, actually. So if we put one of them way over here, put one of them way back here, so it's like an oscilloscope. So you can see that each of these points has like sinusoidal motion, right? In this case, instead of plotting the wave itself, can you tell that it's just plotting the height of that one point? Can you all tell the difference? So like over here, it's plotting. Can I zoom out? I can't zoom out. Sometimes these things have zoom settings on them. What it's showing you here is that each of these points is moving through, well, what would you call that kind of a wave right there? I mean, it's almost just a perfect example of what? It's a sine wave, right? Yeah, sine wave, cosine wave, whatever you want to call it. So the interesting thing here is that the only difference between the points over here compared to the points over here. Oh, look, I got them to be in phase now. That's what I was trying to do. That's good. So now these 2 points are exactly in phase with each other, right? Because when, I mean, yeah, it's hard to tell, but if you look on here, it's hard to tell, but if you look on here, it's really easy to tell. What's the difference between the gray points and the black points, though? How would you describe the difference to someone if you're trying to describe it? The points over here compared to the points over here. The amplitude for one of them is greater, right? The gray one is greater, right? Because it's going kind of off the screen, right? All right. I guess we could also make this so they were exactly 180 degrees out of phase. Move this far enough right here. It's close. Did I go too far? Maybe I went too far. That's pretty close. It's weird because they're different heights. I think that's pretty close, actually. So these would be 180 degrees out of phase with each other. Now, I've put this one up here just to mention something. These 2 waves at this point and this point, if you were to add them together on this little picture right here, they would kind of always be exactly opposite to each other. Do you see that? If we ignore the amplitudes for a second, the height of this wave and the height of this wave are always exactly, I think you could say -1 times the other one. It's exactly the opposite, right? You know what I mean? It's like this one's negative here and this one's positive. And then we get to here, this one's at its bottom while this one's at its top. They're always exactly the opposite position to each other in terms of phase. This is something that's going to come up when we talk about interference of waves later on when we add multiple waves together. Okay, so let's take this off here for now. Let's see what happens to... So here's my next question. So we know that the frequency of this wave was... Or sorry, we know the amplitude of our wave here. Or no, this is wavelength, right? The wavelength of this wave is 2 centimeters now, right? And I asked you to tell me what's going to happen once we increase the frequency, and many of you correctly said that the wavelength was going to get shorter. There's always an inverse relationship between wavelength and frequency. If you increase frequency, wavelength goes down, and vice versa. What about the amplitude, though? So the amplitude is what? Amplitude is how big these crests are, right? How high they go above the equilibrium position, right? Okay, let's turn off the pulsing. I just mentioned that this is the equilibrium position here, and the waves basically modify that, right? So as we send a single pulse through here, the wave creates, this is called the pulse that travels along here. The amplitude is basically the height of the pulse at any point. And you can see the amplitude gets smaller and smaller and smaller as it goes along here. And again, this is because the wave's losing energy. Because we're farther and farther away from the disturbance over here. So the question now is, if I were to decrease the amplitude here, what effect is that going to have on the frequency that we see here and the wavelength that we see? Is the wavelength going to get shorter, longer, or stay the same if I change the amplitude? Let's say that I bring the amplitude, I'll increase it to maximum is what we'll do. Ooh, that's nice. I like that graph. What do you think? If I increase the amplitude to maximum here, what's going to happen to the wavelength? Is it going to get longer, shorter, or stay the same? Longer, hopefully longer. Think about it. What do y'all think? Everyone put an answer down. And now what I want you to do is to think about what's actually happening here and try to relate it to something that you've seen before. So this wave right here, right? The thing that I always connect this to is I remember playing with things like hoses and electrical cables, like power extension cords and stuff like that when I was a kid, or strings. So imagine that you, instead of dropping water in here, we replace the water with a string, okay? Maybe something like this. Go this way. And imagine that you just take a string and you whip it like this. Have you all done that before? Where you take like a hose or something and you take one end of the hose and you like whip it and you see like a little pulse travel down like that? Is that something you all have experienced before? You take like a hose or an extension cord or a string, or like I was saying earlier, like a sheet or a towel or really any piece, any kind of object, and you just like give it a pulse like this, right? Okay. And when you do that, you probably, maybe you remember, maybe you don't, there's kind of a speed at which the wave, this is a wave, right? Remember, a wave doesn't have to be continuous, okay? It doesn't have to be like this. A wave is just, you got a medium, which is a string, you send a disturbance down the string, and it moves down. That's a wave, okay? We would call that a single pulse, right? Here, that's one pulse, right? One pulse. That's a wave as much as this is a wave, okay? All right, so the other thing I want you to think about is think about how fast the wave moves down the string when you do something like that. And maybe you can try this after today's lecture's over or during break or something. Go find something in your home that is long. Again, it could be a sheet, it could be a towel, it could be a string. I think a really good thing to use is like, if you happen to have like really long extension cables, like those orange ones that are really long, that's a really good one to use. A hose is a really good one to use, but you kind of have to lay it out on the ground. And I want you to think about how fast the wave moves compared to how hard you whip it. Does that make sense? Like a big pulse or a small pulse. And I want you to look at what I'm doing right here and tell me, what do you think? Does it look like the size of the pulse matters for the speed? So there's the speed with a small pulse. There's the speed with a big pulse. Do they seem any different to you? Or do they seem about the same? To me, they seem about the same. We could even time it. I don't know how easy this is to do. Here, let's see. Let's turn on the pulse one. If I put these right next to each other, I can probably time it. That was 1.6 seconds. And then I can increase the amplitude. It's hard to time. It's definitely hard to time this. It looks like it's about the same, whether you have this amplitude or this amplitude. Stop, reset, click, click. Wait. Oh, because the amplitude's 0. It has to have some amplitude. So here we go, stop, stop. I think it's about the same. Okay, so back to the original question, which was, we go back to here, oops, here. This one, waves intro, okay. The question was, I'm going to increase the amplitude. What effect does that have on the frequency? A few people seem to think that the wavelength would get longer. Some people seem to think it would stay the same. So let's see what happens. So we'll increase the amplitude to maximum. We'll push play now. Can't really tell much of a difference over here of the amplitude. I guess it's a little bit higher in these waves down here. But if we now pause it and we look at the wavelength is in fact the same. So the wavelength only changes if you change the frequency, not if you change the amplitude. And the velocity of the wave, which is directly connected to the wavelength and the frequency, also doesn't change when you change the amplitude. Okay? So let's write down some of the math for this real quick, and we'll come back to these demos here in a bit. So when you have a wave, let's say we have a sinusoidal kind of wave like we were looking at a second ago, we can define things such as wavelength, which is the distance between here and here. We use the symbol lambda for wavelength. So lambda is wavelength. The wavelength is directly related to the frequency and the speed of the wave. So the frequency of the wave we call f. And this is the rate per second at which these crests pass by a given point. And we can also define what's called the period of the wave. These waves are, after all, very periodic in nature. And there's a connection between all of these things here. On this picture right here, I can't really draw a period, can I, on this picture? But what we can say is that the velocity, so wavelength is the distance between two successive crests. And so this is a crest. This is a trough. A crest is a maximum, a trough is a minimum. We can define amplitude as the height of the wave relative to the axis. So the amplitude could be A or negative A down here. So A stands for amplitude. That's going to be the size of the wave. The bigger the amplitude, the bigger the energy. If you see a wave coming across the ocean and it's just kind of a small wave and it crashes on the shore, that's a low amplitude wave which carries low energy. But if you were to see a giant wave coming to the shore that was about to crash, maybe it's down near somewhere where you're watching people surf or something like that, the higher the wave is above the water, the more energy it carries, because of course when it hits the shore, it's going to crash into the shore, and all that gravitational energy from its weight is going to fall into the shore. So the higher the amplitude, the more energy it carries. And there's a connection between the wavelength and the frequency, which is that the velocity of the wave is equal to the wavelength multiplied by the frequency. Or you can say it's equal to the wavelength divided by the period, because another thing we can say is that the frequency of the wave is equal to 1 over the period. The period is the time it takes for one oscillation of the wave. Okay. All right, so those are just some basic definitions of what a wave is. We can now talk about types of waves. And this is kind of shown in this picture right here. We classify waves into two different types, although some can have a little of both. There are transverse waves. This is waves in which the motion of the medium. What is the medium again? The medium is things like water, string, air, earth, snake. The medium, the thing that's doing the waving, is perpendicular to the wave speed. That's a transverse wave. Motion of the medium is perpendicular to to the wave speed. Okay? This is kind of shown over here in this picture, where when you send a wave down a string by moving your hand up and down like this, the string goes up and down, which is up and then down, so that's perpendicular motion, the pieces of the string. But the wave itself, the pulse, travels along the string. That's a transverse wave. This is a transverse wave, because the motion of the medium is up and down, so perpendicular to the speed of the wave. The speed of the wave goes to the right. You can see the wave is traveling this way. One thing to mention about the motion of a wave compared to the motion of a particle, for example, is that this wave, it doesn't actually move the water anywhere. You know what I mean? This is an even better example. Hey, let's make this a fixed end here and send a very small amplitude. So these are the pieces of the medium, right? And when I send a pulse down here, make this a little bit bigger. When I send a pulse down here, notice that the string doesn't go anywhere. You know what I mean? The string is still sitting right here. It hasn't gone anywhere. It's just sent this pulse down its end until the pulse ran out of energy, right? But the string didn't go anywhere. The string just moved up and down. So that's where we understand how it's transverse motion. The medium is moving up and down. The wave is moving to the right, so we call that a transverse wave. Okay, so that's a transverse wave. This is a transverse wave, and most of the waves you probably think about are transverse waves. So motion of water, waves through water, waves through a string, even some portion of an earthquake's waves are transverse. The other type of wave, which is indicated down here in the middle, is called a... I need to turn this thing off because it's making a lot of sounds. Okay. The other type of a wave is called a longitudinal wave. Examples of this are sound waves and waves on like a slinky. And you can guess that in this case, the motion of the medium is parallel. Or in the same direction as the wave speed. The type of drawing that I always see show up in textbooks is something like this here, where you have this piston that's moving back and forth, and it creates regions of compression and rarefaction, or like high density, low density regions, and the fluid particles basically just shimmy back and forth like this. On this, we can show that with this here. I don't know that this is really going to be any different than what we already saw, is it? I mean, this looks exactly the same. It's just that there's a sound device here, so I don't know if this is particularly useful. So maybe I have to try to draw this. So the idea here is that they've got their picture here, but I don't know if that picture is very clear to you. So let me try to draw something here. All right, so let's take a little tube. And let's say that inside of this, we've got on one end, okay, wait. You know what's even easier to describe? Let me see if I can just find a picture of this, because there's not a picture of this in your book. But, let's see if I can find a picture of it. So you can have a longitudinal wave on a spring, as they're indicating right here. See if I can find a picture, or maybe even a way. There we go. This picture's great. This is a great picture. And this is even better, probably. Okay, so longitudinal wave on a spring. You take a spring like this. This is something when we have lab this week, right? I can show you this in lab class. So suppose you take this spring, right, and you take a little piece of it and you just pinch it closer on this side, right? So you create a little compression of the spring, right? If you let go, that compression will actually travel along the spring. Okay, so like you squeeze one into the spring and then you let go of it. Can you all imagine what I'm talking about? Does that make any sense at all? You've got this spring, maybe you hold it between you and another person. You take a piece of the spring and you just squeeze it a little bit and then you let go. What'll happen is that place where you squeezed it, where you created what they're calling compression here, will then propagate along the spring, and that compression will basically kind of like travel along the spring like this, okay? And there'll be areas of the spring that are compressed, areas of the spring that are not compressed. They call that rarefaction, and yeah, there's a few different examples of this here. Maybe this picture is a little bit better. So you imagine that you're moving your hand back and forth in this direction, and then as a result, this little compressed region will kind of travel along, right? So start here, you compress it, and then you stretch it, and you compress it again. And so you can see that there's like an uncompressed, a compressed region, and then an uncompressed, and then, yeah. Is this something you can visualize? Is this something you've seen before? Have any of you seen this before? Where you take a spring like a slinky or something like this and do this? I don't think this is a natural thing someone would do with a slinky. But anyway, you can visualize it at least. Okay, I'll show you in class on when we have our lab on Wednesday, if you remind me. It's very easy to do. Okay, so that's what we call a longitudinal wave. Motion of the medium is parallel to the wave. Now we can connect this to sound waves, because the way that sound waves are produced, they're longitudinal waves, and they're made through the air, and the thing that is compressing and expanding is the air itself. So when we talk about the longitudinal wave of sound, which is the whole next chapter is on sound, we're going to find that it's high pressure and low pressure regions that indicate what's happening with the sound wave. And what happens with your ear, you'll remember we did this problem, let's just go back to just personal experience. You'll know that if you get into the ocean and you swim down, that pressure increases. We've learned all about that in this class, right? The deeper you go in the ocean or a lake or any body of water, pressure increases, right? And where do you normally feel that pressure increase? So let's say you get into a pool, you swim down to the bottom of the pool. Where do you notice the pressure increase usually? Around your eardrums, in your ears, yeah, exactly. And I think at the time I told you all that your ears are really sensitive to pressure variations. So a sound wave is a longitudinal wave basically of air pressure. And as the air pressure gets denser or less dense, your ear can tell. And it's like there's this little vibration that's occurring in the air itself. And from that vibration, your ear hears that and turns it into sound, right? It picks up on these subtle fluctuations of pressure, and that pressure wave is what a sound wave is. And it works kind of like this. It's a kind of longitudinal wave where, like when I'm talking, right, there's something that's vibrating when I'm talking, right? What is it called? I'm really bad with biology. What is the thing at the back of your throat that like makes sound? Your larynx. I don't know. But the idea is that, well, I mean, I guess this drum is a really good example, or this speaker is a really good example now that I think about it. If we go to back to that speaker, how do I get back there? Here we go. This one. I mean, this thing is what a speaker has, something that basically just like moves in and out, little diaphragm here that goes in, out, in, out, in, out. And it propagates waves of pressure, okay? Yeah. What happens when I play tone? Oh, that's the tone, and we can change the frequency. In terms of sound frequency, you just hear high frequency as high pitches, and low frequency as low pitches. Are you able to hear the sound that's coming out of this? You probably can't, actually, unless I share the... Are you able to hear that sound at all? No? Okay. I probably have to share the... that's not a big deal. Anyway, okay. So longitudinal waves. Transverse waves, two different types of waves. Okay, so now what we want to do now is to talk about... what's next? The wave function for traveling waves, I think. How we're going to actually describe these things. Do I have a problem? I have one... Did I put this problem on here? No, our first problem is 15.1. Okay, 15.2. Okay. Alrighty. I put this picture on here too, which is directly related to what we're talking now, actually. But so let's start talking about that. Okay. All right, so we're going to be talking about the wave function for a traveling, and we often use sinusoidal waves because they're the simplest to kind of analyze and the easiest to do math with, and the thing that you're most familiar with. But I want to emphasize that waves do not need to be sine waves. It's not required that waves be sine waves. So our goal is to say, suppose that I have a situation like what is shown here, where I have a string similar to the string that we had in this wave on string thing. By the way, if you want to find this is at a website called PHET, and you can play with it yourself if you want to, but what we're going to be looking at are waves that look like this. Let's turn the frequency down. No, let's turn the frequency up, actually, because we want to be able to see a couple waves on here. All right. This is the kind of wave motion we want to describe now. And actually, we're going to be talking about a wave that doesn't damp out, so we're going to do no damping. So that is going to be our traveling sinusoidal wave. This is what we want to describe. We want to come up with a wave function, which is going to describe the position of the string at any moment in time. So we want to come up with some function y of x and t, where y is going to be the dimension up and down, x is going to be the left and right dimension, and then obviously time is going to be the dimension that is engaged when we push the play button. So at any moment in time, if we stop time, we'd like to be able to describe the shape of the wave right? At some moment in time, t equal to 0 seconds, t equal to 1 second, t equal to 2 seconds, whatever, right? At any moment in time, we could freeze it, and we could tell you exactly what the shape of the wave was, right? Obviously, it's a sine wave, right? But if, let's say this is x equal to 0, then, you know, here, let me push play again for a second. I'm trying to get it so that it doesn't really stop right when I push pause, so I have to stop a little early, I guess. Okay, like right there. If we stop time right there, right? And I said that this is the, up and down is the y-axis, right? Left and right is the x-axis. And I tell you this point right here is the origin. The point where the pulse is happening, right? The oscillator. What type of function would describe this right here? Would it be a sine function or a cosine function? Again, this is the origin. Here's our function. I want to write down one function as a function of x, just y as a function of x. This would basically be y is equal to sine of something times x. It could be sine of something. We're gonna use sine of k times x, but y equals something times x, right? And multiplied by, on the outside, some amplitude, right? So this function right here, if I come back to my picture right here, would look like y equal to a times the sine of x, right? Where a just represents how tall it is, right? So if amplitude, in this case, amplitude is 0.59, right? So that would be, this number right here would be 0.59, that number right there. 0.59 centimeters times the sine of x, right? But now, say that we allow some time to pass. You know, say a little bit of time goes through, and now the wave looks like this. And let's say that this is like half of a period later, or something like that. It kind of looks like that's what happened. Now it's no longer y equal to sine x, right? What would this one be? So this could be, for example, like t equal to 0, right? And then now we maybe go to t equal to, I would think that it's half of a period or so that I moved forward. What is this one going to be? It's not a cosine function now. It's negative sine, that's right. So at t equal to -2, we get y equal to -a times the sine of x. Okay, so can you see that this function alone will not describe the motion of our wave, right? And this function alone won't describe the motion of our wave. But this function, each of these, describes the shape of the wave at a moment in time, right? Would everyone agree with that? It's the shape of the wave at a moment in time. Because after all, we paused time to even look at what it looks like. Because what does the wave really do? It does this. Oh, we can go slow motion. That's kind of nice, actually. This is really what the wave's doing. So y as a function of x alone will not do it, right? So the wave function, what we're looking for at least, needs to be y as a function of x and time, so that at any point in time, we can actually know exactly what the wave looks like, right? Okay. So in the picture over here on the left, the times that I've written here don't exactly line up. Because here, what's happening is that the starting point for this wave at t equal to 0, what kind of wave is that? If it starts at maximum here, at t equal to 0, what kind of function is that? Is that a sine function or a cosine function now? It's cosine now, right? Okay, so here, what we're seeing is that t equal to 0, our wave is y equal to cosine of x, right? And then, now this one steps through the period by 1/8 of a period. So if we want to get to negative cosine x right here, that's going to occur way down here at 4/8 t, where now it's going to be negative cosine x, right? T over 2. And after one full period, which is the time that it takes to get back to the original position, here we are back at the original position again. What are these dots on here for? What are you noticing about these? If I look at the dot over here on the left, what do you notice about it? Is it moving to the left or right? Is that dot moving to the left or right, or is it just staying still? This dot right here. Is it moving or is it staying still? It looks like it's staying still, and we can check that if we put a little line right here. And yeah, it looks like they're all in the exact same location. I need to hold the Alt button for some reason, but oh, this isn't even straight. It's pretty close to straight though. I can't ever get these things to be straight unless I zoom. There we go, that looks straight. Okay, if I put this on top of here, you can see that every single dot gets hit. That's to indicate the fact that the pieces of the medium are only moving straight up and down. This is a transverse wave, right? All these dots line up completely here. I do that because I think these dashed lines here can look kind of confusing. But what they're trying to show you with the dashed lines, what's the same as you look inside of these dashed blue lines they put here? What are they trying to get you to see there? The negative cosine wave? It's just the cosine wave, yeah. The cosine wave, right? That is a cosine function right there, right? Pretty much, right? It's a little pulse of the wave, and it's saying that that distance is the wavelength, and it says the wave advances by 1 wavelength lambda during each period t. Right? So if we look at where the wave was at the start of the period here, that piece is now here, because the pulse has shifted from its peak being here to its peak being here, right? The pulse moved, right? We can see that on here if we pick like, let's say we pick that point right there. We can see a full wave here. If we let one period flow, then this pulse will have moved to this point right here. So if you look at that pulse between those 2 points, we let time go through. It's so hard to do. Eventually, we're going to be here again, right? It repeats itself. That's the whole point, is there's a periodic pattern, right? So 1 period is the time it takes for this thing to go from here, down, back up, and then there again. And once it gets back to there again, now you're back to that same waveform of this sine wave right here, right? So again, the idea is that after 1 period, this will have moved up. It's already going down right now, right? Is it going down? Here, let me do this again. Okay, so 1 period is the time it takes for this object right here to go down to the bottom, back up to the middle, up to the top, and then back down again. Just the same way we described the period of like a pendulum in physics 1A, right? A full motion. And after 1 period, we're right back to that exact same waveform again. Does that make sense to everyone? That's 1 period. The wave has moved 1 cycle forward. Okay. So how are we doing on time? We're fine. Okay, so we want to be able to describe the motion of our wave. And what we can say is that we know that if we look at if we combine this position to this position here, right? We know that, let me get rid of the U. We can say that y at x equal to 0, okay, at some point in time t, right? So at the point x equal to 0, this is x equal to 0 right here, all the way up to the top, that's x equal to 0. At x equal to 0 and time t, we know that that point obeys a cosine function, right? This is what I was trying to tie it back to the... Do you all remember, I don't know how well you remember this, in physics 1A you learned about simple harmonic motion, right? And you learned that simple harmonic motion basically obeys a function like this, right? Obeys a function like this. So if you're talking about the motion of a pendulum that's moving back and forth, and you describe where it is at any moment in time, you can use a cosine function to describe that, to describe the angle that it makes as a function of time. If you talk about a box on a spring, you can use a function like this to describe the motion of the box on a spring. And in this case here, coming back here, let me go to make this a cosine function. If I look at this piece right here, right? what I'm trying to say is that if you watch just that single piece, you're going to notice that one piece moves up and down with simple harmonic motion, right? So if we put, can I get a ruler or, okay, I can get a reference line. I can get a ruler, okay. Here, so just watch that one point. Having a ruler here I think helps. If we just watch this one point right here, we'll notice that it basically moves up and down with simple harmonic motion. So let's watch this green dot right here. Ignore the other wave. Would you agree that the motion of that single dot is basically just simple harmonic motion? Straight up, straight down, straight up, straight down. Just like the motion of a pendulum. This would be like a pendulum that was oscillating down and then up and then down and then up. Would you all agree with that? So that we can make this statement right here? Okay, so we know that this point, right, moves up and down with simple harmonic motion. And we also know that the same thing is going to be true. Well, we know that this has to basically repeat itself so that every period you get the same kind of, expression for the motion right here, right? And in order to do that, we want to be able to say that this is going to have the same value when we move one period over, or sorry, yeah, one wavelength over. Sorry, when we go to this position here, so at x equal to lambda, we should get the exact same function, right? That is to say that if I write this as y equal to, whoops, y of x equal to lambda, comma t, this should be exactly the same, right? That's to say that the motion of this point right here is going to be the same as the motion of this point right here. Does that feel right to everybody? Here we can compare it by doing that dot and a dot that is exactly one wavelength farther, which is basically this dot right here. The idea would be that if we look at the green dot on the left here and the green dot here, they're pretty much in sync with each other. It's like not perfect, but they pretty much are. I could manipulate the frequency and stuff until they were, but the idea is that when the left dot is crossing the middle, the right dot's crossing the middle. When the left dot's at a minimum, the right dot's at a minimum. When the left dot's at a maximum, the right dot's at a maximum. So these two mirror each other, right? Perfectly. Always doing exactly the same thing. It's not exactly perfect, but it's pretty close. Does that make sense? And where would that point be? Well, that would be exactly one wavelength, because it's the distance between this point and this point. That's one wavelength, right? So we know that the two functions have to match up perfectly. It's the same function, but it has to repeat itself pretty much, right? All right. So how do we turn that into a function, right? How do we take this idea and get x into our function, right? Okay, so we need something that when we plug in lambda is going to cause the phase, the piece inside of here, we call the piece inside of here, we call this the phase. And so basically what has to happen is that the function of x and t needs to work such that that the phase repeats itself every lambda, right? So for this function, the phase has to repeat itself. Every lambda and every period t, okay? So in order to do that, we need to multiply by something inside of here. We need to have some kind of function, and it needs to be some function of x and t. And inside of the cosine part, right, you need to multiply by something so that you get the same value whenever you multiply by lambda. So if we have some x in here, and we have some t in here, and we know that t has an omega on it. I didn't say what omega was, I should have, I'm sorry. Omega is just frequency, where you multiply by 2 pi. So 2 pi times the frequency is omega. If you remember simple harmonic motion, you probably remember this, but I should never assume that it's been a long time, so you probably don't remember all this stuff. So this is in radians per second, is what this is measured as. And it's related to the period as t, what is it, 2 pi divided by t. Okay, so that's what omega is. I should have mentioned that, I'm sorry. I could have written this as 2 pi times f times t. Okay, so we know there's an omega t in here. We need to have something multiplied by x so that when I multiply by lambda, it repeats itself, right? So if we were to just take out the omega t part for just a second and think about what has to happen for the x part, like let's say, for example, we make this really simple on ourselves and now we look at t equal to 0 because we did the same thing over here. How do I get this to repeat itself? I need to do a times the cosine of something times x, and I need to have it repeat itself. Well, if you know anything about cosine functions, you know they repeat themselves every 2 pi, right? So what can we multiply by inside of here to make it so that when I put a value of x in here, that it repeats itself every whole number multiple of the wavelength? Does that make any sense? So when I put a times the cosine of lambda in here, I guarantee that I get the same thing as when I get a times the cosine of 2 lambda. These need to be the same as each other, okay? What do I need to multiply by here? Let's say that let's give it a number, let's give it a variable. Let's call it b or something. What does b need to be equal to in order for this to happen? Oh, and when I look at this, yeah, we still need to have the b in here as well. B here and b here as well. What does b need to be so that we can make this true? Just look at these equations here, these bottom two. What does b need to be equal to? What is the only way that these two could be equal to each other? What value of b would make them equal? I think there's 2 answers. No, there's only one answer. Is it easier if I do pi? Oh, let's try pi. Let's see what happens, okay? So if I put a cosine of pi lambda is equal to a cosine of 2 pi lambda, and now we got to have a value for lambda or we can't even check our answer, right? So let's say a equal to 1 to keep things simple, and let's say that lambda is equal to, let's just use 5. I don't know if that's a good number or not. I don't know, 5 meters, okay? Then would this work? Would a times 5 pi be equal, so this would be a will become cosine of 5 times pi. The right-hand side would be the cosine of 10 times pi. I think that would work, right? Those two should both be equal to, I don't know if it's going to work. What do you all think? Is that going to work? Put it in your calculators and check it. Put your calculators in radian mode and check. Is the cosine of 5 pi the same as the cosine of 10 pi? Pretty sure it's not. I think one's -1 and one is +1, right? I think you all should kind of know before you even do this, right? But maybe you don't. I don't know. What do you all think? Are they equal to each other? Do you check it? I think the one on the left is -1 and one is +1, right? Yeah, because it's a positive. Cosine of 0 is 1. Cosine of 2 pi is 1. Cosine of 4 pi is 1. But the cosine of pi, 3 pi, etc. Troy, did you use degrees? That's not correct. No, that's not right. As I said, you need to put your calculator in radians mode. Okay, so pi doesn't seem like it works, but it's close, because if this is -1 and this is +1, well, then what if we just use 2 pi? Yeah. Okay, so if we have 2 pi in here, then we would have on the left-hand side cosine of, well, if lambda is 5, then we'd have 10 pi over here, and we'd have 20 pi over here. And this would work, because this is going to be +1, and this is going to be +1 because it's an even multiple of pi. Okay, so we know that we need to have something related to 2 pi, right? We need to have something related to 2 pi. So if b was equal to something like 2 pi, then it might work. Now the problem now is that x is a variable that can take on really any values at all. And really what we need to do to make sure this is guaranteed to work out is we're going to have to divide this by lambda, so that our y of x and 0 is going to have to be something like a times the cosine of 2 pi divided by lambda times x. So why did I divide by lambda? Well, in the example that I gave you here, I picked a value of lambda that was 5 or something like that, right? And make sure that I'm getting off the, yeah, okay, we're doing this right. Now if we pick any value of x, we want it to be the case that the quantity inside of here, the phase, right? This is the phase. We want it to repeat itself every lambda, right? Not just every random variation of x that happens to give you an even number, right? Or a whole number, right? So if we don't, here, what I'm trying to say is this. If I remove the lambda right here, when is this going to be equal to, so at what values of x, y of x comma 0 equals, let's say 1, that would be the maximum, right? Or even clearer, we'll do a, for what x? My God, I can't type today. When is, if we just put, if I just write it like this, we know we need a 2 pi in here, right? But if I just write it like this, what values of x are going to give y of x and 0 equal to a? Oh, we need to take a break. Why don't you try it yourself? Let's take a break right there. Think about that during the break. If I give you this function right here, you can either test this by using your knowledge of trig or whatever, or you could just plug and chug, right? You could like try different things here. So put your calculator in radians, try different values of x. For what values of x are you going to get a here? Okay, we'll take a break for 10 minutes. We'll start again at 11:01. Think about that while we're on break. Function